Welcome everyone, my name is Ryan Corey. I am the session chair of this session. This session is titled Lightweight Backfill. A couple things to note before we start the presentations. You will have the opportunity to ask questions during this on-demand session by clicking question buttons at the bottom of the video window. Your questions will be sent to the presenter to answer as soon as they are able. To claim PDH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey of any sessions that you attend. Please note that you will need to include the verification code shown in this session to verify that you did attend this session and ensure that you receive the proper credits. Please enjoy the presentations.
Hi everyone, my name is Hao Liu, a PhD student at the University of Kansas. The title of my presentation is Reduction of Lateral S Pressures Behind Retaining Walls Using EPS Foam and Geosynthetics Reinforcement. This presentation will include introduction, test setup and materials, test results, and conclusion. Introduction. For conventional design methods, the lateral S pressure is assumed to increase with the depth. However, there are some drawbacks for this method. First, lateral S pressure distribution behind a retaining wall depends on many factors, such as height and stiffness of the wall structure, backfill properties, wall movement model. Lateral S pressure distribution behind the retaining wall is often nonlinear due to soil arching when the retaining wall has some movements. Lateral S pressure near the top surface can even reach up to the Rankine passive state due to compaction. There are three methods to reduce the lateral S pressure for the retaining wall. The first one is using compressive inclusion to allow more lateral movement in the backfill. The second one is using some materials such as geosynthetics to reinforce the backfill. The third one is using inclusion and geosynthetics together. However, in the previous research, the wall was not permitted to move during the backfill replacement. After backfilling, the wall was moved intentionally to study the relationship between the lateral S pressure and the wall movement. But in this study, the wall was permitted to move during the backfill replacement. Test setup and materials. This figure shows the test setup for the physical model test in this study. The retaining wall was supported by the footing connection and the manual jack. Two displacement transducers were used to monitor the wall movements at the height of 0.15 meter and 0.99 meter. 5 S pressure were attached to the back facing of the retaining wall to monitor the lateral S pressure during the backfill replacement. This equation is used to calculate the flexibility of the retaining wall. The value of 3.0 means that the retaining wall is pretty rigid compared with the backfill material. For this study, in total, 3 tests were conducted. For test T1, no EPS and no geogrids were used to reinforce the backfill, and this test is the control test. For test T2, EPS were placed behind the retaining wall, and the 5 S pressure were attached to the back facing of the EPS foam. For test T3, EPS and geogrids were used to reinforce the backfill, and the length of the geogrid is 75 centimeters. Kansas River sand was used as the backfill. The backfill was compacted to achieve the relative density of 75%. The unit weight of the backfill is 18.05 kilonewton per cubic meter. The peak friction angle is 42.2 degrees from the direct shear test. Biaxial geogrids were used to reinforce the backfill. 2 ribs per 4 ribs were cut off to simulate the uniaxial geogrids commonly used in practice. The thickness of the EPS foam is 1 inch. The minimum compressive strength of the EPS foam is around 70 kPa. The density of the EPS foam is around 16 kg per cubic meter. Test results. Those two figures show the wall movement during the backfill replacement. From those two figures, we can see the wall moved away from the backfill during the backfilling. When the EPS was used, the wall movement of this test were almost same with the control test. The reasons for this phenomenon may be that the thickness of the EPS foam was just 1 inch, and the elastic modulus of the EPS foam was not too low compared with the elastic modulus of the backfill material. The wall is just 1.05 meter high, and the compaction effect was small. Therefore, the EPS had limited effect to reduce the wall movement. From those two figures, we can say that the geogrid had a significant effect to reduce the wall movement. The reasons for this phenomenon may be that the geogrid can restrain the natural movement of the backfill. Therefore, the backfill will apply less lateral S pressure to the backfacing of the retaining wall. This figure shows the lateral S pressure behind the retaining wall after backfill replacement. From this figure, we can see that the lateral S pressure near the top surface will be larger than the at-rest pressure. The reason for this one is because the compaction will cause additional lateral S pressure. The lateral S pressure near the bottom will smaller than the at-rest pressure. The reason for this phenomenon is that the wall moved away from the backfill. Therefore, the lateral S pressure near the bottom will decrease. This figure shows the force to hold the retaining wall in place and the lateral S pressure from the backfill. The force to hold the retaining wall in place was monitored by the node cell. For the lateral S pressure, we assume it will increase with the depth. The moment caused by the force to hold the retaining wall in place and the lateral S pressure relative to the toe of the retaining wall should be zero. Then we can get this equation to calculate the K value. The second figure shows the change of the K value with the height of the backfill. From the figure, we can see for the control test, the K value will largest. For the test with EPS and geogrid, the K value will smallest. Conclusion. Use of EPS only slightly reduced backfilling effects on wall. Combined use of EPS and geogrid more effectively reduced backfilling effects on wall. Compaction induced additionally lateral S pressures within the upper portion of wall. Movement of wall away from backfill reduced lateral S pressures within bottom layers to even lower than at-rest S pressures. Thank you. Any questions about this presentation?
Hello, thank you for watching this presentation. My name is Teresa Anderjack Laux. Today I'm going to be talking to you about ultra lightweight foam glass aggregate as MSE wall backfill. We're going to talk about properties of the foam glass as well as some MSE wall case studies where foam glass aggregate is utilized. I would like to acknowledge my co-author, Archie Filschel, as well. This slide shows you a brief outline of what we're going to be talking about during this presentation. I'll start out with an introduction, and then I'll go into talking about the properties of ultra lightweight foam glass aggregate as MSE backfill. Then we'll talk about stability of MSE walls, both internal and external, and additional considerations when you're using lightweight materials such as ultra lightweight foam glass aggregate in MSE walls. We'll finish up with some case histories. We're going to be talking about a project along I-95 in Philadelphia, Pennsylvania, and another project, the Route 6 and 10 reconstruction in Providence, Rhode Island. The photograph that's on this slide is just a picture of foamed glass. The ruler that you see at the bottom is a 12-inch long ruler. So you can see the particles are generally on the coarser side of things, on the order of 1 to 2 inches in size, with a surface texture that would be similar to pumice stone. There are frequent instances that might warrant the use of lightweight fill materials within an MSC wall. This may be because of soft, compressible soils underneath of the wall, or because of existing utilities or structures. Some current lightweight fill materials on the market include expanded shale and clays, EPS geofoam blocks, cellular concretes or foamed concretes, and ultra-lightweight foam glass aggregate or ULFGA. So I want to tell you a little bit about this relatively new product and how it is made. The first step is that recycled glass cullet, that's mixed color, comes into the manufacturing plant and has to be cleaned. This is because of many impurities making its way into the glass stream due to single stream recycling processes. The next step that you see in the upper right photo is that 3/8 inch or so sized glass cullet has to be milled to a very fine powder. After that fine powder is mixed with a foaming agent and sent through a very hot kiln that gets up to 1,000 degrees Celsius. When the material comes out the back end of the kiln, it looks like what you see in the bottom left photo. It's a solid foam glass cake that starts to crack up by the time it reaches the end of the cooling table because of the thermal stresses that are induced from being in a very hot kiln to then exiting to room temperature air. Ultra-lightweight foam glass has some inherent environmental advantages because it's not a material that is mined and it's not petroleum-based. Also because it is so lightweight, on the order of 15 pounds per cubic foot dry unit weight, it's able to be shipped in very large truckload deliveries, so up to 100 cubic yards or 75 cubic meters. So this can greatly eliminate the total number of trucks and truck traffic coming to a project site. Mechanically stabilized earth systems are a popular and economic option to construct retaining walls for highways or railways, wing walls and abutments for bridges, and numerous other applications for both public and private development. An MSC system is generally comprised of alternating layers of fill and reinforcement materials. These reinforcement materials are generally polymer-based, also known as geosynthetics, or they are made of steel. There are 2 leading resources that provide design guidance on MSC systems. They are shown on the slide. In terms of MSC backfill specifications, again, there are numerous specifications that are available, but the most stringent has been published and put forth by AASHTO in the LRFD bridge construction specifications. So that is what I'm going to be comparing the properties of ultra-lightweight foam glass aggregate to. The photograph in the bottom right of the slide, you can see a MSC wall being constructed with galvanized steel straps. The first properties that I want to talk about are actually not mandated by the AASHTO LRFD bridge construction specification for MSC wall backfill. And these are unit weight and buoyant unit weight. So the minimum and maximum in-place unit weight for foam glass can be considered to be 15 to 23.5 pounds per cubic foot. So this should be used in any type of load or surcharge calculation where, for example, you're trying to calculate the effect of raising the grade over existing ground. So, for example, we might be considering the situation shown in Figure A to the proposed condition shown in Figure B. For projects that are going to be constructed near waterways where the foam glass aggregate layer could potentially be flooded and submerged, a buoyancy check should be done on the material. This is because most foam glass aggregate that is intended for infrastructure use, is a closed cell foam glass, which means that it is going to be slightly buoyant. The buoyant unit weight determined through testing has been found to be on the order of minus 15 pounds per cubic foot. Applying a factor of safety of 1.5, that leads to a design buoyant unit weight of minus 22 pounds per cubic foot. So the situation shown in figure C should be checked to make sure that in the event of a flood, the buoyant force from the saturated foam glass is counteracted by the cover material and unsaturated part of the layer above the flood elevation. The next properties that I'd like to talk about are gradation and plasticity. So for the gradation requirements put forth by AASHTO, you can see those in the table, as well as the light blue shaded area on the figure. There have been grain size distributions completed on both pre-compacted and post-compacted foam glass aggregate. Those are the grain size distribution curves that you see on the figure. And you can see that foam glass clearly resides within those AASHTO limits, both pre and post-compacted. AASHTO also has a maximum plasticity, and foam glass aggregate is non-plastic due to its chemical composition of recycled glass. In terms of strength requirements, AASHTO would like any MSC wall backfill materials to have a friction angle of 34 degrees or greater. Large box direct shear testing completed on foam glass aggregate indicates friction angles between 41 and 55 degrees, depending on the confining stress. The figure shown on this slide shows you a schematic of using foam glass aggregate as the entirety of the reinforced fill in an MSC wall. In the design of any MSC wall, we will want to check the internal stability of the wall by looking at the factor of safety against the reinforcement pulling out and the reinforcement breaking. These calculations are used to determine the reinforcement spacing, the reinforcement length, and in the event of a wrap face wall, the overlap distance. External stability of MSC walls also has to be considered. This includes analyzing the wall for overturning, sliding, and a global or foundation failure of the wall. To complete both internal and external stability evaluations, earth pressures due to the retained soil, any type of surcharge loads, or live loads have to be considered. Occasionally, the setup that I just showed you on the previous slide may lead to issues satisfying internal or external stability factor of safety requirements. And so 3 potential adjustments that can be made to the MSC wall are shown on this slide. The top figure shows you a combination of both foam glass aggregate as well as typical unit weight reinforced fill. In this situation, you could be increasing the factors of safety because of the additional weight of those normal weight soils, contributing to higher stress levels on the reinforcement materials, and also adding more bulk to the entire mass, and so helping external stability calculations. The schematic shown in the bottom left shows you reinforcing elements being extended into typical unit weight reinforced fill. All right, and again, this benefits internal and external stability by increasing the stress on the reinforcing elements and increasing the total weight of the reinforced mass. The third adjustment that I'm showing on the bottom right figure is by including foam glass in the sloped area as retained backfill. And when this is done, the lateral earth pressure from the retained backfill is also greatly reduced because of the lightweight and highly frictional nature of the foam glass aggregate. Some additional considerations when using foam glass aggregate in MSC walls are shown on this slide. They are primarily related to installation, drainage, and dynamic stress considerations. So in terms of installation, foam glass is installed using a method specification. It does allow up to 2 feet thick maximum lifts if installed and compacted using tracked equipment, or 12-inch lifts if using a plate compactor. So these lifts may need to be adjusted based on the proposed spacing of reinforcement. Additionally, drainage from the foam glass can be accounted for, but foam glass aggregate in general will be very freely draining because of the coarse particle sizes. Additionally, there are some dynamic stress considerations that foam glass has similar to other lightweight materials. So it's not unheard of for there to be, say, 3 to 4 feet from the top of pavement to the top of foamed glass aggregate. This could be to account for moment slabs, traffic barriers, or fencing, or just to minimize the dynamic stress on top of the foam glass layer. You'll also notice black fabric shown wherever foam glass is going to be in contact with another granular material. In general, this is recommended to prevent intrusion of fines into the foam glass aggregate layer over time. Compaction is generally 10 to 20% of a given lift thickness, and this has been verified through a LiDAR compaction research study, as well as numerous test strips for DOTs across the Mid-Atlantic and New England. The first project I want to tell you about is a project for the Pennsylvania DOT along I-95 just north of Center City, Philadelphia. This project involved staged construction of a newly constructed or reconstructed on-ramp to southbound I-95. So you can see in this photo the existing on-ramp shown on the right-hand side of the photo. This on-ramp is founded on columns that are supported by deep foundations. The new on-ramp is being switched from being a bridge structure to being an embankment. And because of this, the DOT and the designers working for the DOT were worried about using normal weight fill in this embankment structure and what that would do if underlying soils were compressed, and that applied lateral stresses to the existing deep foundations for this ramp. The DOT did specify that this ramp had to remain in service for the entirety of the project. So this ramp is being constructed as a geogrid reinforced structure. The contractor did have a selection of what they wanted to use for their supportive excavation design. You can see the foam glass aggregate being stockpiled in this photo. The total ramp height is about 30 feet high, and the lightweight materials were only used in the section adjacent to the columns and deep foundations of the existing ramp. This figure shows you a cross-section of the reinforced ramp. You can see that the reinforcement ties into a cast-in-place wall on one side, and then it has temporary facing consisting of steel welded wire mesh facing units on the opposite side. And finally, we have some photographs from the construction of the MSC wall. In the upper left, you can see that there was some stormwater piping that had to be integrated into the reinforced fill. In the upper right, you can see that existing ramp and columns, and you can also see the temporary facing for the foam glass aggregate section consisting of that welded wire mesh. In the bottom left, you can see the biaxial geogrid reinforcement that was used, and you can also see that they used a geotextile wrap on that temporary facing so that material didn't fall out of the larger openings of that welded wire mesh. And the bottom right is just showing you as the ramp was being built up adjacent to that cast-in-place wall. The second case history that I want to share with you today is the Route 6 and 10 reconstruction project in Providence. This was Rhode Island DOT's largest design-build project to date, and the section that utilized foam glass aggregate is related to two flyover ramps. And the reason that lightweight fill had to be used within these ramps is because of a large diameter 100-year-old brick sewer and some challenging subsurface soils. The utility owner told the DOT that no additional loads could be imposed on the subsurface utilities by the embankment. This figure shows a typical cross-section for both of the flyover ramps on this project. I'll draw your attention to a couple items. You can see that the shaded blue area was the required undercut in order to provide a zero net surcharge on the underlying utility and soils. Also notice the shorter stems of this U-wall system extending into the backfill material. The reinforcement that was used is a geogrid in combination with some polymer straps. Another item to notice on this cross-section is the moment slabs on top of the foam glass aggregate. This is in order to accommodate the traffic barriers. This slide shows you two photographs from the ramp construction. You can very clearly see the biaxial geogrid that's used as reinforcement in the right-hand photo. That excavator that's shown is the primary equipment that was doing the placement and compaction of the foam glass. And finally, we have another aerial photograph showing you the completed ramp about halfway up to the final abutment height. The final abutment height for this ramp was about 36 feet. Now I'd like to conclude and thank you for listening to this presentation. I hope you learned a little bit about using ultra-lightweight foam glass aggregate as MSE wall backfill. If you have any questions at all, please, first of all, see the paper for much more detail than I was able to share with you today. And if your questions still aren't answered, please don't hesitate to find me on LinkedIn or through the Aero Aggregates website. Thank you so much. Bye-bye.
Hi, my name is Mandi An-Naddaf. I'm a PhD and lecturer at the University of Karbala and formerly a PhD student at the University of Kansas. I'm presenting on behalf of my advisor, Professor Jihan from the University of Kansas, my colleague Mustafa Rahman Najadi from Torakon, my colleague Sajjad Rashid from the University of Karbala. Our presentation title is Effect of Geoform Geometry and Location on Vertical Stresses on Buried Culverts during construction and intersurface load. The outline for our presentation would be a short introduction, followed by the problem statement and objective for our research, and then we will go through the experimental test that was conducted for this study, and followed by the numerical modeling that we did for our study. And then we will present some results and conclude our presentation. So just a quick reminder, the title for this research was the effect of geoform, geometry, and location on vertical stresses. So actually, when we have buried structures such as pipe, culverts, and many more under road, especially when the road is shallow, we expect high pressure transferring from the traffic to these buried structures. The higher stiffness of this buried structure can affect the distribution of load and may increase the pressure on the structure, which will result in defect in the structure and along the long run. However, using geosynthetic, such as geoform, particularly above the structure, can protect the structure and provide and reduce the pressure on the culvert or pipes. This method called is induced trench installation method, and we will discuss it more throughout the presentation. To understand the conceptual vertical stress distribution over a buried structure, the figure on the left side of the slide shows that when we have no buried pipe or structure, we would have almost a uniform distributed pressure under the overburden pressure. While when we have a stiff pipe under a traffic loading, the pressure distribution would be like the one with the dotted line. Higher pressure on the pipe and less pressure on the side, and this is due to the soil arching, the negative soil arching. On the other hand, when we have a deformable pipe, we would have less pressure on the middle of the pipe and higher pressure on the side of the soil, and this is due to the positive soil arching. So what is soil arching? Soil arching is defined as the transfer of stresses from a yielding area onto a joining stationary area throughout the development of shear stresses, as given by Terzaghi in 1943. So the two construction methods that we have relating to culverts are the positive projecting impactment, in which the culvert are put and the column on the top of the culvert has less settlement than the surrounding soil. So the surrounding soil are subjected to more settlement, and then the load will increase on the culvert. The second installation method, it's the induced tranche installation method, when we have a compressible layer above the culverts, and the column, the soil column above the culvert in this way will be more deformable than the surrounding soil due to the presence of the compressible layer. So the soil arching will be positive soil arching, and the pressure will transfer away from the culvert and result in a reduction in the pressure on the culvert. For this study, the problem statement was limited studies have been conducted to evaluate the response of a buried structure installed under a relatively low fill height by the ITI methods, especially under surface loading. Surface loading can affect the pipe and increase the loading on the pipe. Also, limited studies have been carried out to investigate the effect of EPS geoform geometry, including its thickness, width, and location on the traffic load distribution above the buried structure. So actually, the objective for this research was to assess the effect of geoform thickness, width, and location on a buried box culvert using numerical analysis using Plaxis 3D software after simulating the experimental test and verifying the model. So the first part of our study was the experimental test, and the left side of the slide showing in the figure on the left side of the slide, we're showing the experimental test layout in which the box culvert are buried in the middle of the box, and then we have on the top it a geoform layer, and there's several pressure cells on the top of the culvert and also on the top of the geoform and the surrounding soil. And it shows the footing also on the top of the embankment where it's centered along the center line of the box culvert, and it has the same width as the box culvert. The test that we conducted, and here we are simulating for this study, are two tests: the positive projecting impactment test, in which no geoform were used, and the induced traction installation method test with EPS 15 and geoform thickness of 0.2 BC. The sand that was used is Kansas River sand, and it is a poorly graded sand. The geoform that were used are EPS 15 and with the following specification. So from the experimental result, what we're seeing here that in the case of no geoform, the PPE, positive projecting impactment, we have higher pressure above the culvert, especially in the middle, which reached about 75 kPa vertical pressure. However, when we used geoform above the culvert, we reduced the pressure by about 10 kPa in the middle of the culvert, in which it was about 65 kPa. This is under a loading of about 130 kPa. So using geofoam, even with a thin layer of 72 millimeter or 0.2 from the BC. BC is the width of the culvert. It can reduce the pressure on the culvert and transfer it away to the surrounding soil. So for our study in which we said we're gonna verify the model first using Plaxis 3D and then simulating several problems to investigate the thickness of the geofoam. For our study, we used 0.2 BC, 0.4, and 0.8 BC. So all the height or the thickness of the geofoam are in terms of the width of the culvert itself, and also we investigated the width of the culvert. So we have 1 BC and 1.5 BC and 2 BC, in which it's showing on C geofoam width, the figure that show the way that we simulated it. And also we investigated the location of the geofoam. So we moved the geofoam layer higher than the culvert by 0 BC, and then by 0.2 BC, and then by 0.4 BC above the culvert. I won't go in details for this slide, but what I'm gonna say, for our numerical modeling using Plaxis 3D, we used hardening soil models with the specification that, or the characterizing that shown in this slide. For the impactment soil, which was Kansas River sand, and we use Mohr column model to simulate the geofoam. And also we used linear elastic models to simulate the concrete culverts and steel footing, with the details shown in this slide. Here's we're showing on the left side of the slide the model verification result for the positive projecting impactment in which no geofoam was used. So here we're showing the experimental and the numerical result. As we can see under the applied footing pressure, the pretty good agreement between the experimental and numerical result for the positive projecting impactment as the pressure increase, as the footing pressure increase. Also on the right side of this slide, we're showing the induced tranche installation method with the geofoam EPS 15, and also we can see the an acceptable agreement between the result of the experimental and the numerical result. It's good to mention here that we didn't, even though we're showing the pressure agreement for the model verification, we did not rely on this condition only, but also we tried to verify the model with the behavior of the footing settlement, geofoam compression, and also the overall behavior between the two impactment for the experimental and the numerical part. So proceeding with the result of our numerical analysis, in this slide we are showing the effects of geofoam thickness on the pressure distribution or the vertical stress distribution on the bare structure. And on the left side of this slide, we are showing the behavior during construction. So as I mentioned before, we investigated the three thicknesses for the geofoam: 0.2 BC, 0.4 BC, and 0.8 BC. And as we can see from the left side figure, we can see that using 0.8 BC reduce the pressure. It has the highest reduction in the pressure on the culvert. during embankment construction. However, on the right side of the slide, as the applied footing pressure increased from 0 to about 100 kPa, we see, so in the start, we see some difference between the pressure on the culvert, but as the pressure increase, the footing pressure increase, the applied footing pressure increase, we see like almost the line coming together, and they are meeting at 100 kPa. So at low applied pressure, we can see some effect or some contribution from the thickness of the geoform, but as we go along increasing the footing pressure, this effect kind of comes together similar to that of 0.2 BC. From this, we can conclude that using 0.8 BC or increasing the height of increasing the thickness of the geoform, it can reduce the pressure on the culverts. This slide also compares the 4 conditions that we simulated in this study and showing also the geoform thickness effects. Basically, in this slide, we are normalizing the pressure in regard to the no geoform condition. So the no geoform condition, it's 1, and using geoform of 0.08 BC, we see a reduction at an applied pressure of about 0 kPa or before applying any pressure. And this reductions reduced as we increase the applied footing pressure, reaching of about 50, like 0.92 or 93. So basically, there's about 0.07% reduction in the pressure at 100 kPa. However, it was about 32% for the 0.8 BC condition. This slide shows the effects of geoform width. And basically on the left side of this slide, we conducted the 3 conditions in which 1 BC, the geoform width was 1 BC, the 1.5 BC and 2 BC. During embankment construction, we see there's almost no effect of the width of the geoform width on changing or reducing the pressure above the culvert. However, as the applied footing pressure increased, as shown in the right side of the slide, we see like the one with 1 BC, the test with 1 BC has the least pressure increase on the culvert. So we conclude that the having a same size of the geoform as the culvert can reduce the pressure effectively. So this figure shows the normalized pressure on the culvert for different condition of geoform width. The same conclusion we reach that when we have a geoform same size as the culvert width, we would have the most effective reduction or the most reduction on the culvert in terms of vertical pressure. Here we're showing the effect of geoform location, and basically the conclusion is when we have the geoform closely or directly placed on the culvert, it will have the highest reduction of the load or the pressure on the culverts. Again, this figure also showing that having no space between the geoform and the culvert, it can reduce the pressure more effectively than the condition of 0.2 BC and 0.4 BC away from the culvert for the geoform. So in conclusion, the use of EPS geoform reduced the vertical pressure on the culvert due to the mobilization of positive soil arching. Also, less vertical pressure was applied on the culvert as the geoform thickness increased from 0.2 to 0.8 BC during the embankment construction. However, the vertical pressure on the culvert increased and reached the same value for all geoform thicknesses under the application of footing load as we seen previously. The geoform width, larger than the culvert width, had no effect on the vertical pressure on the culvert during embankment construction. However, it caused a slight increase in the vertical pressure on the culvert under footing. Also, the geoform that was placed at a farther vertical distance from the culvert transferred more pressure to the culvert. In summary and overall, after the investigation of the geoform thickness, width, and location, it can be concluded that a thick geoform with the same width as the culvert and directly placed on the top of the culvert is the most effective geoform geometry in the vertical pressure reduction. Thank you for your attention, and please, if there's any question, go ahead.